So today we are going to solve some more problems based upon the free body diagrams. Let us see this problem. So four blocks of same mass connected by strings are pulled by a force F on a smooth horizontal surface as shown in the figure. The tension T1, T2, T3 will be. So this is very simple problem. Can you tell me what will be the tension? Alright, so this is a smooth horizontal surface. Okay, that means there is no friction, and if you can see this, there is this force F. Okay, it is acting on these four masses. So what can I say? The net force is equal to what? Four masses, m plus m plus m plus m. Okay, 4m times, this is the total mass multiplied by acceleration. Okay, now you can start drawing the free body diagrams. So if I talk about this last mass, okay, so this mass is m and acceleration is a. So the tension acting on this mass is T3, right? It is T3. So what can I say? T3 is equal to m multiplied by a. So how much is it in comparison with this force? Compare it with this force F. Force is equal to 4m times a. T3 equals to m times a. So force is 4 times compared to T3. So T3 equals to F by 4, I can say. Similarly, if you take this second mass, okay, so on this second mass, T2 is acting on this side, T3 is acting on this side. Okay, so this is T3, this is T2. All right, so T2, I can say force acting on this one also. It is m into a, because all of the masses will have same acceleration. Okay, so force acting on this one is also m times a. So m times a is equal to what? The force in or the tension in direction of force minus this tension. Okay, so it is T2 minus T3. So how much is it? So how much will be T2? Take T3 on other side. So you get T2 equals to MA. Okay, you get T2 equals to MA plus T3. That is 2 times MA. Okay, and in comparison with force, how much is it? It is F by 2, right? And similarly, you can find out T1. So for this mass, okay, or you can take this mass or this mass to find out T1, right? So if you take this mass, the force acting on it on towards right is T2, force towards left is T1. So how much will be T1 minus T2? So T1 minus T2 is also m times a. Okay, so take T2 on left hand side. So you get T1 equals to what? T2 plus MA, that is 3 MA, and that's equal to what? MA is equal to F by 4, right? So this is equal to 3 times F by 4. This is simple. Okay, so what is the answer? T1 is 3 times F by 4, T2 is F by 2, T3 is F by 4. So option C is the answer, right? Option C is the answer. This is very simple problem. See, there are two masses, 10 kg and 20 kg respectively. They are connected by a massless spring as shown in this figure. Okay, a force of 200 newtons acts on 20 kg mass. At the instant shown in the figure, 10 kg mass has acceleration of 12 meter per second square. The value of acceleration of 20 kg mass is. This is the question. So we can draw free body diagram. So if we think about 10 kg mass, okay, what is the force acting on it? Only F, right? And its acceleration is given. Okay, its acceleration is given is 12 meter per second squared. So how much would be F? It is this mass multiplied by acceleration. Okay, so it is 10 multiplied by 12. So 120 newtons. And if you think about the second mass, 20 kg mass, what are the forces? One is the spring force acting towards left. Okay, and one is this 200 Newton force. Right, the spring force will be equal and opposite. Okay, so for 20 kg mass, it will act towards left. And we have found it out. It's 120 newtons. So how much is the net force acting on this 20 kg mass? Let's suppose its acceleration is A. So m into A is equal to this 200 Newton minus F. Okay, 200 minus F is 120 and mass is how much? It is 20. So 20 times A is 200 minus 120, which is 80. Right. So A is equal to 80 by 20. So 4 meters per second squared. Option A. Right. This is simple. The next problem is, now there is some complexity. Okay, little bit complex, because there is friction. The coefficient of static friction mu s between the block of mass 2 kg and the table as shown in the figure is 0.2. So coefficient of friction is given. What would be the maximum mass value of block B? What would be the maximum mass of B so that two blocks do not move? Okay, they are not moving. The string and the pulley are assumed to be smooth and massless. The string and pulley, they are massless. Okay, so this is again a simple question, right? So if you think about this block B, it's not moving. That means what are the forces acting on it? One is the tension in the string, and other force is what? Its weight downwards. Okay, so if it is not moving at all, that means this tension acting upwards is equal to mg, right? So you can say T is equal to mg. Okay, and how much is its mass? That we have to find out, right? Okay, what is the mass of block B? That we have to find out. So it is, let's suppose, m. So T is equal to mg. And for this block A, now there is tension T acting towards right, and there would be another force. So if it tends to slide on this floor, there will be the frictional force acting towards left, right? And how much would be the friction? So friction is equal to mu multiplied by normal reaction. Okay, and if this one doesn't move, then this friction must be equal to the tension, and tension we have found, it is equal to what? Mg. Okay, so this is equal to tension, which is equal to what? Mg. Now mu multiplied by normal reaction. So what is normal reaction? Because this is horizontal surface, the normal reaction is equal to weight. Okay, so how much is weight? So its mass is 2 kg. So weight would be how much? 2 multiplied by 10, and it is equal to mg. Right, it is equal to mg. Okay, you can cancel out this 10 and g, or you can substitute g equals to 10 and you can cancel it out. So this gets cancelled out. So m is equal to mu times 2. So how much is mu? How much is mu? 0.2. Right. So it is 2 times 0.2. 0.4. 0.4 is the answer. Option D. Okay, this is clear. So a system consists of three masses m1, m2 and m3 connected by a string passing over a pulley P. The mass m1 hangs freely and m2 and m3 are on rough horizontal table. Okay, so these are on rough horizontal table. The coefficient of friction is mu. the pulley is frictionless, so pulleys are frictionless and of negligible mass. The downward acceleration of mass m1 is. So now there is some acceleration. Okay, so that we have to find out. All right. So we can bundle up these masses m2 and m3 because we don't care what happens in between these two masses, right? So m2 and m3 we are bundling up, and there is some tension in the string T acting towards left. So how much will be the tension in the string? That we don't know it, we have to find it out. Okay, so there is some tension in the string, and since this is a rough surface, there would be some frictional force acting towards right. Okay, so suppose there is some frictional force F acting towards right. So how much would be their acceleration? So we can say the total mass. Total mass is m2 plus m3. Right, this is the total mass. m2 plus m3 multiplied by A. This is the net force. Net force is towards left. So it is total force towards left minus total force towards right. Okay, so it is equal to what? T minus F, the frictional force. And how much would be the frictional force? Mu multiplied by, yeah, but what is M? M is m2 plus m3. Right, friction is acting on both of them. So, okay, so total mass is m2 plus m3. Okay, so it is m2 plus m3 multiplied by A is equal to T minus mu multiplied by mg. So m is m2 plus m3 multiplied by we have g. So let's call this equation number 1, and then let's draw free body diagram for m1. So what are the forces acting on m1? There is gravitational force m1 times g, and there is tension in the string which will be equal to this tension. Okay, so here what can we say? That it accelerates downwards, and that acceleration will be same as that of this acceleration. Okay, because the whole system is connected. So acceleration is A, so the net force will be downwards, and how much would be that? So net force is m1 times A, it's equal to m1 into g minus tension in the string. So this is your equation number 2. Okay, and then you add 1 and 2. So what do you get? The tension will get cancelled out, right? Tension will get cancelled out, and you get m1 into A plus m2 plus m3 times A is equal to, on right hand side you have m1 times g and minus, okay, m1 times g minus mu times m2 plus m3 times g. Okay, and all the masses are equal, so you can substitute that also. So m2 plus m3 will be what? 2m. Okay, this is equal to m. Okay, so this is 3m. So 3m times A is equal to m times g. So you can take m common also. M times g minus mu times 2 times m. m2 plus m3 is 2 times m multiplied by g. You can cancel out m from everywhere, and then you want to find out the acceleration. So take 3 on the other side. So it is g minus mu times 2g divided by 3. Or you can take g common. So what do you get? Which option? If you take g common, you get 1 minus 2 mu. Option C, right? Okay, so this one also was simple problem, right? All right, so let's move on to the next one. Okay, a block A of mass m1 rests on horizontal table. A light string connected to it passes over frictionless pulley at the edge of table, and from its other end, another block B of mass m2 is suspended. Okay, so there is block of mass m1. It raised on horizontal table. Connected to it is a string which passes over this pulley, and from that string, another mass is connected, which is m2. It is suspended, right? It's suspended. The coefficient of kinetic friction between the block and the table is mu k. Okay, so mu is suppose the coefficient of kinetic friction when the block A is sliding on the table, the tension in the string is. So this is exactly similar to the last problem, but in this case we want to find out the tension. Okay, so let's find out tension. So let's draw free body diagram of M2. So for M2, the gravitational force is acting downwards. So it is M2 times G. Tension is acting upwards, T. Okay, so net force will be M2 times A is equal to total downward force M2 times G minus the tension. Okay, similarly, let's call it 1 second. So consider mass m1 and there is some friction acting on this mass m1. So frictional force acts towards left F and towards right is the tension in the string. Okay, tension in the string. So the net force is m1 times A. You can say m1 times A is equal to tension in the string. Okay, tension in the string minus what? The frictional force. And how much will be frictional force? Mu multiplied by the normal reaction. And how much will be the normal reaction? It's equal to its weight. Okay, so mu multiplied by m1 times g. This is equation number 2. So if we add these two, what do we get? Tension gets cancelled out, right? Tension gets cancelled out. So we get m1 plus m2 times a on left hand side. It's equal to what? M2 times G minus mu times M1 into G. And if you move this M1 plus M2 times A towards right, you get the acceleration. Okay, so you get the acceleration A is equal to M2 times G minus mu into M1 times G divided by M1 plus M2. And substitute that in first equation or second equation to find out the acceleration. So let's put in the first equation. Okay, sorry, to find out tension. So T equals to, what is tension? This M2 into G minus M2 times A. Okay, if we substitute that, what do we get? What do we get? Acceleration, we have to substitute. So tension is equal to M2 times G minus M2 times A, and A is M2 times G, M2 times G minus mu times M1 times G divided by M1 plus M2. Okay, so let's multiply and divide this term with m1 plus m2. So it is m1 m2 times g plus m2 square times g and everything divided by m1 plus m2, and let's multiply this one with m2. So minus m2 square g, and this minus minus becomes plus. So it is mu m1 m2 g. Slightly lengthy question. This thing gets cancelled out. M1 M2 you can take common. So M1 M2, okay, 1 plus mu times G divided by M1 plus M2. I think this should be the answer. So it is M1 M2 1 plus mu G divided by option A, right? If plus minus everything is correct, option A is the answer. In the given figure, the pulley is assumed massless and frictionless. this pulley is massless and frictionless. If the frictional force on the object M is F, there is some frictional force, then its acceleration in terms of force F will be equal to. Okay. So for this kind of problem, remember there is pulley, okay, and this end of the string is connected to rigid support. Okay, there is another end which is connected to mass. So now there is tension acting on both the sides. So if you think about the pulley, there is tension in this string T and T, right? And there is force acting towards right. Okay, so now pulley is massless. Pulley doesn't have a mass. So you can say mass times acceleration is equal to what? 0. Okay, so that 0 is equal to, the net force is 0 because mass is 0. Okay, so it's equal to F minus 2T. Okay, F minus this tension plus this tension, 2T, and therefore you get 2T equals to F or T equals to F by 2. You got this? Yes, no? All right. So for question like this, please remember you have to solve, you have to apply, I mean, you have to draw free body diagram of pulley first. Okay, or intuitively you can say F is equal to what? 2 times T, because there are two strings pulling on this pulley towards left and there is this force acting towards right. Okay, so F will be equal to 2T and T will be equal to what? F by 2. Okay, directly you can say. And then you have this mass. What are the forces acting on this mass? So there is one force due to the string, tension in the string, and it's given that there is some friction, small f. Okay, so friction is small f, right, towards left. So what is the net force? T minus F is the net force. Okay, so M times A is equal to T minus F, not capital F, it's small f, and therefore acceleration is T minus F divided by M. And what is T? We have found it out. It's F by 2. So let's substitute that. It is F by 2 minus F divided by M. Is there such an option? Yes. Option B is the answer. Okay. This question is clear? All right. Let's move on to this next question. A block of mass M is in contact with the cart C. There is this cart C and this mass is in contact with this. Okay, this block is in contact with the cart. As shown in the figure, the coefficient of static friction between the block and the cart is mu. Okay, the acceleration alpha of the cart that will prevent the block from falling satisfies. Okay, so that mass is just kept like this, right? The mass is just kept like this, and the cart accelerates like this, and because of that acceleration, the mass doesn't fall. So how much should be that acceleration? Okay, so there are two ways of solving this problem. One is considering the non-inertial frame of reference, and another one is considering the inertial frame of reference. Okay, so we'll use inertial frame of reference first, and at the end I will tell you about the non-inertial frame of reference. Okay, our observer is outside. Okay, so observer is, let's suppose, here looking towards the system. So for this observer, what is the force acting on this mass? It's the normal reaction, right? And because of this normal reaction, what happens? This mass also gets accelerated with the same acceleration as that of the cart. Yes, no? Okay. So therefore I can say the normal reaction which is acting towards right like this, it is equal to what? This mass multiplied by the acceleration alpha. Okay, and if the mass doesn't fall, that means the weight is balanced by the frictional force. So frictional force is upwards. Okay, so how much will be the frictional force? Mu times the normal reaction. Okay, so if it doesn't fall, mu times normal reaction, I can say mg is equal to mu times the normal reaction. Okay, right, weight is balanced by the frictional force. And how much is normal reaction? It is m times alpha. So put that, so mu multiplied by m times alpha is equal to mg. Okay, right? So here, if it doesn't fall, then maximum friction should be greater than or equal to, right, mg. Okay, so mu times n is greater than or equal to mg, we can say. And now we will substitute n equals to what? M alpha. So it is m alpha is greater than or equal to mg, and then this m gets cancelled out. So you want alpha, no? So alpha is equal to greater than or equal to what? G divided by mu. Option C is the answer. So is it clear? So let's see this next question. A block of mass m is placed on a smooth inclined wedge. So this is that smooth inclined wedge, and this block is kept here. Okay, ABC of inclination theta. Okay, inclination is theta, as shown in the figure. The wedge is given an acceleration a towards the right. Okay, it is given some acceleration towards right. The relation between a and theta for the block to remain stationary on the wedge. So how much should be that acceleration? Okay, we have to find out acceleration such that this block remains stationary. This is the question. Okay, so once again, we'll consider our observer is looking from outside. Okay, so our observer is inertial. For this inertial observer, now what are the forces acting on this block? You solved it? G divided by A equals to, no. Wait. I will tell you. See, this block is there. It is stationary. It's not moving. See, now there would be the normal reaction acting on this block, which is in this direction. Okay, and the system is accelerating like this towards right, and there is the weight of this block acting downwards, mg. These are the two forces, only two forces. So you can resolve the normal reaction along two perpendicular components. So if this angle is theta, this angle here will be theta, right? So this one will be 90 minus theta. Okay, so therefore this component is equal to what? Because this is 90 minus theta, it is n sine theta, and this component will be n cos theta. So do you understand this? Okay, you understood the resolution? See, this angle is theta, so this angle will be theta. Okay, this angle is 90 degrees, so subtract theta from 90. So this one will be what? 90 minus theta, and this one will be theta, you can say. Okay, so if this is theta, this is the cos component, this is sine component, right? Okay, so now this mass is also in acceleration because wedge is in acceleration, so this block is also in acceleration, okay, towards right. So here you can say that mg, the weight of this block, it is balanced by the vertical component of normal reaction. Okay, and the block is in acceleration, so that acceleration is provided by the horizontal component of normal reaction. Got this? Yes, no? Okay, so I can say n cos theta is equal to mg, and n sin theta is equal to what? The horizontal force acting on this block due to the weight. Weight is moving like this. Okay, so weight is moving like this. It is exerting some horizontal force on the block. It is m times the acceleration a. So it is provided by what? Horizontal component of normal reaction. And now you can divide first by second or second by first. So n and n will get cancelled out. Okay, so if I divide second by first, I will get tan theta equals to what? Ma divided by mg, that is a divided by g, and therefore a is equal to g tan theta. So g tan theta, option D is the answer. Understood? Okay, so a block of mass m is placed on smooth wedge of inclination theta. Sorry, a block of mass m is placed on a smooth wedge of inclination theta. The whole system is accelerated horizontally so that block does not flip on the wedge. So this is similar to the last problem. Okay, the force exerted by wedge on the block will be. So in earlier case, what was asked? The acceleration was asked. In this case, the force exerted by wedge on the block is asked. Okay, so can you tell me, looking at this problem, what would be the force exerted by wedge on the block? This problem is similar. See, there is this wedge and this block. Okay, so force exerted by wedge on the block is equal to the normal reaction. It is equal to what? The normal reaction. So how much is that? That we have to find out. Okay, so there is another force which is acting downwards. Mg is acting downwards. This angle is theta, and the system is given acceleration a. Okay, so now what we can say here is we can resolve n along two components just like the previous problem. So this component will be n cos theta, because this angle is theta, so this angle will be theta. This is 90 minus theta, so this will be theta. So this component is n cos theta. This other component is sin theta. Okay, and n cos theta is equal to mg, right? So the options are given in terms of mg. So I can say n cos theta is equal to mg, and therefore n is equal to what? Mg divided by cos theta. Okay, it is mg divided by cos theta. Option D is the answer. So see, a mass m is placed on very smooth wedge resting on surface without friction. Once the mass is released, the acceleration to be given to the wedge so that m remains at rest is a, where? Okay, so m is released, m is kept there. Okay, and you are moving the wedge such that m doesn't fall. So how much acceleration should be given? So we had solved this. How much acceleration should be given? A is equal to g tan theta, right? So which option is correct? G tan theta is here, here also. So should it be applied towards left or towards right? Right or left? left. Okay, if you apply it towards right, yeah, Sanjay, if you apply, yeah, if you apply it towards right, what will happen? The block will slide even faster. Okay, it is already falling down, and you are taking this wedge away actually, so it will slide even faster. Okay, you have to exert it towards left such that there will be a normal reaction, right? If you pull it towards left, then only there will be a normal reaction. Got it? Okay, so answer is option A. It has to be applied towards left. Okay, such that it provides some normal reaction. Okay, if you move it towards left with some acceleration, and the horizontal component of that normal reaction provides the acceleration. Okay, provides that acceleration. So then let's look at this problem. A heavy uniform chain lies on horizontal top of table. If the coefficient of friction between the chain and the table is 0.25, then the maximum percentage of length of the chain that can hang over one edge of the table is. So there is a table. This problem is not asked in the NEET exam, but it can be asked. It has been asked in many medical and engineering exams. Okay, other exams. So there is a chain like this. Okay, so I will just pass forward the drawing process. This is the chain. So its one end is hanging like this. Okay, so what's given? A heavy uniform chain lies on horizontal top of table. It lies on the horizontal top of table. If coefficient of friction it's given, then the maximum percentage of length of chain that can hang over one end. Okay, that we have to find out. So let's suppose this length is L, and the total length of this chain is equal to capital L, right? So total length is capital L, and the length that hangs is small l. So how much would be this length? Capital L minus small l. Okay, so this length is this much length. I can say it is capital L minus small l, and we'll consider that the mass is uniformly distributed over the length of this chain. Mass is uniformly distributed over the total length of the chain. So the mass of this part and this part, they are in proportion to their length. Okay, so now let's talk about the part that is hanging. Let's talk about, okay, this part which is hanging, right? So what are, okay, this part which is hanging. So what are the forces acting on this part? I can say there is tension along the chain which is acting upwards, and there is the gravitational force which is acting downwards. So how much would be the gravitational force? It will be equal to mass of this part multiplied by g. Okay, and how much would be mass of this part? If total mass is capital M, is total mass. Okay, then I can say mass of this part is equal to what? The fraction of length multiplied by this mass. Okay, so what is fraction of length? So I can say it is L upon capital L. Okay, this can be 50%, right? This can be 25%, this can be whatever. We have to find out that percent. Okay, so L upon capital L. This length divided by the total length multiplied by the mass. This much would be the mass of this fraction. Sorry, this much would be the mass of this section. Yes, no? And multiplied by g is its weight. Okay, and if it doesn't fall, that means the tension is equal to what? Tension is equal to this, its weight. Okay, L upon L is equal to, sorry, multiplied by mg. So T is equal to sorry, so T is equal to L upon L multiplied by mg if it doesn't fall, right? And what about this? What about this portion? So for this portion, what you can say is there is tension acting towards right, and there is the frictional force acting towards left. Okay, frictional force is acting towards left. So if it doesn't slide, that means the tension is equal to frictional force. Okay, so T is equal to what? Frictional force. And what will be frictional force? Mu multiplied by the normal reaction. And what will be normal reaction? It's equal to weight of this part. And what is weight? It is its mass multiplied by g. And how much would be mass? So fractional length multiplied by the total mass. Okay, so length of this part upon the total length multiplied by capital M. So small l, capital L minus small l is length of this part divided by total length multiplied by capital M. This much is the mass. You got this? So tension is equal to mu times mg. And what is mass of this part? Just like we found mass of this part, okay, it's fractional length, okay, multiplied by the total mass. So fractional length of this part is total length minus this length. Okay, not fractional length of this part is total length minus length of this part. You got this? Yes, no? Okay, so then now weight of this part is equal to tension, and tension is equal to this frictional force. So this is your equation 1, this is equation 2, and you can equate them. So you get L upon capital M, L multiplied by mg is equal to mu multiplied by L minus small l upon L multiplied by mg. And we can see some cancellations here. L gets cancelled, mg gets cancelled. So we get L is equal to, small l is equal to mu multiplied by capital L minus small l. Okay. So I will just erase this part, or let's keep it here. Okay. So we have small l is equal to mu multiplied by capital L minus L. So small l is equal to mu times capital L minus mu times small l. Okay, how much is mu? 0.25. It is 0.25 multiplied by L minus 0.25 multiplied by small l. Take that 0.25 towards left, 0.25 L. So you get 1.25 L, because this is 1 L and that's 0.25 L. 1.25 L is equal to 0.25 capital L. Okay, so you want the fractional length that is hanging. So small l upon capital L is equal to 0.25 divided by 1.25, or you can say it is 1 by 5. Okay, so 1 by 5, 1/5. And if you multiply this with 100, what do you get? L upon L multiplied by 100, because you want percentage. So it will be 1 by 5 times 100, 20%. Okay, now what we'll do is, I will tell you another way to solve problems. That is the non-inertial frame of reference. Okay, so we'll take similar problems, same problems that we took earlier. Okay, so earlier we solved this problem and this problem using which frame of reference? Inertial frame of reference. Now we are going to use non-inertial frame of reference, and you will see you will get the same answer. All right. So see what happens in non-inertial frame of reference. So for an example, you are standing in a bus, okay, and bus suddenly accelerates. Bus accelerates. Let's suppose it accelerates in this direction. What will happen? You tend to fall down like this, okay. So if bus is accelerating towards right, you tend to fall towards left. Can you explain why are you falling? No. So you say that there is some fictitious force, some pseudo force acting on you, okay. So it means there is no force acting, but to explain your acceleration towards left, when bus is accelerating towards right, you tend to fall. If bus is moving toward in forward direction, you tend to fall in backward direction like this, okay. So you can't explain it, this motion, using any real force, okay. You can give justification, but there is no real force acting on you in this direction. So what do you say? You will feel like somebody is pulling you, okay. So you say there is a pseudo force, there is a pseudo force acting on you. So if you apply the concept of pseudo force, okay, some ghost is pulling you, then you can explain this motion, right? Another example, suppose you are sitting in a car and car takes a turn towards left, okay. Car is taking turn towards left. You tend to okay. What happens? You tend to move towards right like this. Yes, no? You tend to fall on the window which is towards right. So this motion also you cannot explain, okay, this acceleration you cannot explain using any real force. So you can say there is a pseudo force acting on you which is towards right. Another example, in circular motion, what happens? The vehicles, they tend to slide towards outwards the circle, okay, outwards of the circle. So if suppose there is a vehicle like this, it's moving on the circular road, it tends to move, tends to slide like this. If there is no friction to keep it on this road surface, it will slide away from the center, okay. So we say there is a centrifugal force, there is a pseudo force acting on it, okay, which in this case we call it as centrifugal force, because this sliding cannot be explained using a real force. So we say a centrifugal force is acting. Another example, which is again for circular motion, that suppose there is a merry-go-round, okay, there is a fair, and have you seen merry-go-round? Looks like this. I mean, there are some, there is a circle, okay, and there are some rods, some animals are connected to, maybe the horses, etc. They are connected to that, okay. So there are n number of them, and this thing, okay, this toy will rotate and you sit on this horse. What happens? So as it rotates faster and faster, this horse and the person sitting on it, it moves away from the center. So it's like somebody is pulling it, okay, somebody is pulling that person away from the center, but you cannot explain it using what? Any real force. So you say that there is some centrifugal force acting on that person, right? So that is the pseudo force, okay. So why is it happening? Why are these people, this person or this car or person sitting in this car, or when car is taking turn towards left, then person sitting there, let's suppose you cannot explain it, okay, that motion using any real force? It's because these are all non-inertial observers. These, all of these observers are in acceleration. This motion is accelerated motion. And the Newton's laws, they are applicable for inertial observer. Okay, so the Newton's laws are applicable to inertial observers. If non-inertial observer wants to explain the motion, he has to take the help of pseudo force. And what is the direction of that pseudo force? So you see here, in case of bus is accelerating towards right. Okay, this person gets accelerated towards left. That means pseudo force is opposite to the acceleration. And how much is its magnitude? Magnitude is equal to mass of the person multiplied by this acceleration. Okay, so to explain this motion, or this motion, we'll take an example. Sorry, we'll take the help of pseudo force. So how much is the magnitude of pseudo force? It is mass of the person multiplied by this acceleration, and it acts in opposite direction of this acceleration. Okay, so let's proceed. Okay, so now let's suppose the observer is here. Okay, so observer is also in acceleration. Earlier we considered observer was here, standing on the road and watching these two bodies. Now let's suppose the observer is riding along with the body. Okay, so observer is also in acceleration. So this system is accelerating towards right. For this observer now, okay, so let's suppose observer is on this block. So for this observer now, there will be a pseudo force acting on him. And what will be the direction of pseudo force? It is opposite to the acceleration we have studied, right? So what will be direction of the pseudo force? The pseudo force acts towards left, because observer is accelerating towards right. The pseudo force acts towards left. Okay, so I will call it FP, P for pseudo, right? And now let's draw all the real forces acting on that person or the block. So what are the real forces? The real forces, the normal reaction due to this cart. Okay, it acts like this. Sorry. And the gravitational force acts downwards, and the frictional force acts upwards. Okay, so this observer says, I am not accelerating, I am at rest. Okay, I am not accelerating towards right, the world is accelerating towards left. That's the perception of the observer who is riding along with the block. Got it? Yes, no? So frictional force is upwards. Okay, so I'm sorry. So for this observer, what did we consider earlier? That the normal reaction provides a force. Okay, normal reaction. Sorry. So for this observer, what did we consider? The normal reaction is towards right, and it's because of that normal reaction that this block also gets accelerated along with the cart. But for the observer who is riding along with the block, so for him, he is at rest, he is not moving. Okay, but there is a pseudo force acting on him. Okay, so it will be towards left. So this is the direction of pseudo force. And what is normal reaction doing? Because the observer is at rest, the normal reaction is balancing that pseudo force. Got it? Normal reaction is, so for that observer, I would say for observer riding along M, normal reaction balances pseudo force. Okay, so N is equal to the pseudo force. And how much is magnitude of pseudo force? We have studied it. It is mass of the observer multiplied by this acceleration. So N is equal to M times alpha, right? And then If the block doesn't fall down, then frictional force is equal to what? Mg. Okay, so F has to be greater than or equal to mg, right? So I will move all of this upwards. Okay, so what is F? It is mu multiplied by normal reaction. And what is normal reaction? It is m times alpha. So mu m alpha is greater than or equal to mg. Okay, gets cancelled. So you get alpha greater than or equal to g divided by mu. So you get the same answer, option C, only change in perception. So earlier we considered this observer who is an inertial observer. Now we considered an observer who is riding along with this mass. Okay, so observer is in acceleration, and that's why for this observer we considered a force which is in opposite direction to the acceleration, called the pseudo force. So is this thing clear? Is the problem clear? Okay, so this is how we solve problems using non-inertial frame of reference. So earlier in this problem also, so what is this problem? A block of mass m is kept on the smooth inclined plane, and the incline is accelerating like this. Okay, so earlier we considered an observer who is inertial. Now we will consider an observer who is riding along with this block. So if this block is accelerating towards right, so for this observer, what will happen? There will be a pseudo force which will act in opposite direction, right? There will be a pseudo force which will act in opposite direction to the acceleration. Okay, so pseudo force acts in opposite direction. So first of all, I will draw pseudo force, and now let's draw the real forces. So this is the mass. Okay, so there is normal reaction acting like this. Okay, the normal reaction acts like this, and there is the gravitational force which acts like this. This is the gravitational force, mg. Okay, now we can resolve the normal reaction along two components. Okay, so I will resolve the normal reaction along two components, this component and this component. So this angle was theta, so that's why this angle is theta. Alternate angles, right? This angle is theta, this is 90 minus theta. Okay, so if this is 90 minus theta, this is theta. So this is cos component, n cos theta, and this is n sin theta. So for this observer who is riding along with the block, who is accelerating along with the block, what is this n sin theta doing? So for this observer, there is pseudo force acting on the observer, right? Which is towards left. So there is pseudo force acting on the block towards left. So this n sin theta is balancing that pseudo force. So observer says, I'm at rest. Okay, I'm not accelerating. The world is accelerating in opposite direction. So why am I why am I at rest? It's because of the pseudo force is balanced by this component of the normal reaction. Okay, so again you get same equations, same set of equations. So pseudo force is how much? It is mass multiplied by acceleration, and it is equal to n sin theta. Okay, and how much is n cos theta? So n cos theta is equal to mg. Okay, or I can say mg is equal to n cos theta. And again you divide these two, so you get a by g is equal to tan theta, or a is equal to g tan theta. So again nothing changed, only the perception. So for this observer, what was the normal reaction doing? What was the horizontal component of normal reaction doing? So this observer looks at the block and he sees that the block is accelerating. Okay, so block is getting accelerated because wedge is in acceleration. It exerts a normal reaction on the block. Okay, and the horizontal component of that normal reaction provides acceleration to the block also. Okay, so for this observer, the horizontal component of normal reaction is providing acceleration to the block, while for the observer who is here riding along with the block, accelerating along with the block, what is the horizontal component of normal reaction doing? It is balancing the pseudo force acting on him, and that's his reason that I am at rest. Okay, there is pseudo force acting on me, which is towards left, and the normal reaction, horizontal component of normal reaction is balancing that pseudo force. So all the forces acting on me are balanced, and that's why I'm at rest. Got this? Okay, so there are two ways to solve problems, motion problems. One is using non-inertial frame of reference, and one is using inertial frame of reference.